Hello and welcome back to Dr. Logic Awkwardly Does Logic. In the previous video, I told you how to identify the variables that occur in predicate logic terms. In this video, I'm going to tell you how to identify the variables that occur in predicate logic formulas. Now, on the one hand, this is actually very easy. You look at the formula, you identify the terms in it, you figure out what variables occur in those terms, and those are the ones that you have in your formula with another clause for the quantifiers, which we'll get to. But it's not just being able to identify what the variables are in a formula that matters. We are also going to introduce another distinction. We love distinctions. And this is going to be between variables that occur bound and variables that occur free. So this distinction has to do with whether or not variables occur under the scope of a quantifier. Now, the important thing is that one and the same variable can have different types of occurrences. So in one part of a formula, it could be bound by a quantifier. In another part, it could be free. So previously, we were just interested in what are the variables. Now we are interested not just in what the variables are, but their occurrences in a formula and whether they are bound or free. So in order to define this formally, we're going to get some more set theoretic definitions. So get your bucket thinking head on. We are going to have various buckets, one for variables, one for free occurrences, one for bound occurrences, and we'll be putting various things in the buckets in a recursive fashion. So first I will define what the set of variables, bound occurrences, and free occurrences are in an atomic formula. And then we will expand this to the more complex formulas. So let's get up our whiteboard. Here we go. Definition, and this is free and bound variables. Pick an arbitrary predicate logic formula phi. So let phi be a well-formed formula in some quantified language LQ. Then, as I said, think of sets as various buckets that we put things in, and this is how you determine what goes in what bucket. If phi is atomic, then we will define the set of bound variables of phi, which we will just write as bound phi, is the empty set. And the set of variables of phi is going to be the same as the set of freely occurring variables. So var phi is the set of all variables, bound phi is the set of bound variables, and free is the set of free variables. And this just is going to be take all of the variables in term one. Oh, nah. Let me erase this so that it is nicer to read. Okay. Take all the variables in term one and union them together with all of the variables that occur all the way up to term tau n, where tau 1 to tau n are the terms occurring in phi. So there have to be at least some terms because phi is an atomic formula, and atomic formulas are made up out of applying relations or predicates to terms. So we know that phi has at least some terms in it, and the variables that are in the atomic formula just are the union of all of the variables in the terms involved. So our set of bound variables is empty, and all of our variables are free. Now, if phi is of the form not psi, then the variables of phi just are the same as the variables in psi. The presence of the negation doesn't change anything. The bound occurrences in phi are the same as the bound occurrences in psi, and the same for the free occurrences. So negation doesn't change anything Doesn't add variables, doesn't remove them, doesn't make them free or bound if they weren't already. If phi is of the form psi or chi, psi and chi, or psi implies chi, then what you do is you just take the collection of the variables that occur in each of the components. So then the variables of phi just are the variables of psi union the variables of chi. So everything from the var psi bucket and everything from the var chi bucket get dumped into the var phi bucket. The bound occurrences in phi are just going to be the ones that were bound in psi or bound in chi. And same for the free variables. So the free variables in phi are the same as the free variables in psi, along with the free variables in chi. Now, at this point, you might think this is not very interesting. Everything seems to be the same as it was, and the way that we started, none of our variables were bound. So why don't we end up with completely free variables? Well, that's because of the quantifiers. The point of the quantifiers is that they pick out a certain set of the variables in the sentence that they scope over or that they range over. So that this is what allows us to be able to say we are talking about everything or about something, some particular thing, as opposed to just kind of waving our hands and saying things. So let's consider that case. If phi is for all x psi or exists x psi, then something interesting happens. The variables of phi are, well, it's all the variables in psi along with the variable that comes with the quantifier, x. Now, in a lot of cases, x may already be one of the variables occurring in psi, but it might not be. But we need to add, we're kind of putting that in there. It is now a variable that is in this formula. The set of bound variables in phi is then going to change. This is how we actually get variables moving into the bound set. It's going to be everything that was already bound in psi along with x. But if we're going to make psi, or if we're going to make x a bound variable in phi, then it can't be free anymore because of the context. The quantifier is now kind of sucking it up into its power, into its scope, and it no longer can act freely. It has to act in accordance with how the semantics of the quantifier will dictate. Don't worry, we'll get to semantics in a couple more videos. So the free variables of phi are going to be the ones that were free in psi subtracting x. So recall from way back when, what, video 4 or 5, when we talked about some basic set theoretic notation, this backward slash is set minus. So we're taking everything that is in the free variables for psi bucket, and we are pulling x out of it, and we are putting it into the bound bucket. And there you go. So every, let me just note a fact. From this definition, it follows that the variables of a formula will always be calculatable by taking all of the bound variables and all of the free variables and putting them together. There are no variables that are not bound or free. I can actually give a proof of this, and I might in a later video, but I might also not because it's really kind of boring because it's just check the definition, check the definition. The other fact is that every variable is either free or bound, but some of them can occur both. Now, I think I'm probably going to draw this video to a close, but the next one, I will give an example of how you can actually, I'll give you a predicate language formula, and we will calculate what goes into each of these buckets. So the variables, the bound variables, and the free variables, and you will see that there's going to be overlap between the bound variables and the free variables because we are interested in the occurrences of those variables. Does this particular variable occur within the scope of a quantifier or not, or both? So there's the definition of free and bound variables. And from this, you also get that you now know how to calculate all of the variables that occur in a well-formed formula. Isn't this just exactly what you wanted to know how to do today? It'll get even more fun in the next video when we put this definition into use. So join me then. Until then, cheers.